We have finished all of the material in this calculus class, and now we're getting ready to take an end of the chapter 7 test this weekend. A big test coming up on Tuesday next week with all the material since our last exam, and then a final exam coming up a week from then. So I wanted to first start with reviewing from chapter 7 and then kind of go back to sketching curves of a graph. And when we were sketching curves of a graph, that would be a great reminder on how to find where things are increasing, decreasing, concavity, max, mins, and pull everything kind of together. So integration, let's just kind of go through this really quickly. And I'm just going to read through this. And what I'm pulling up right now is actually the end of the chapter. They have a great summary of that chapter and a lot of the important theorems and rules that you've been using. So you can always find this in your textbook off of the homework program that we use. Okay, so the summary says early chapters dealt with the derivative, one of the two main ideas of calculus. This chapter deals with integration, the second main idea. There are two aspects of integration. The first is indefinite integration and finding the antiderivative. And the second is definite integration, which can be used to find the area under a curve. The fundamental theorem of calculus unites the two ideas by showing the way to find the area under the curve is to use antiderivatives. Substitution is a technique for finding antiderivatives. Numerical integration, which we actually didn't look at, can be used to find the definite integral by finding antiderivatives is not feasible when it's not feasible. The idea of the definite integral can also be applied to finding the area between two curves, which was the last thing that we looked at in here. And so we looked at the indefinite integrals and indefinite integrals rules that are below. We have that general power rule. We have the integration of x raised to the nth power. That's dx is equal to, we just added one to the exponent and divided by our new exponent. If it was an indefinite integral, we added the c. If it was a definite, meaning there was bounds on top and bottom of our integration sign, then we didn't have to add that constant. The other thing was that this rule did not work when n was equal to -1. If we had n was equal to -1, we had 1 over x dx. And this is equal to the natural log of absolute value of x plus c, which I'm sure is going to come down right here. We had that constant rule, so we could pull the coefficient in front of the integration if we wanted and just integrate the piece without that number in front and then multiply it by that number. We had that sum and difference rule, just like we did with derivatives. We can do that with integration. If we were integrating the exponential function and it was just e to the x dx, well, we knew that the derivative of e to the x was just e to the x. So the antiderivative, what we could take the derivative of to get our integrand is just e to the x plus c, if it's indefinite. But if we had some coefficient in front, k times x, in that exponent of our e value, then we have to think about what we're going to have to undo when we take the derivative so we get this back. And so we have to divide by that coefficient in front of the x and the exponent. So it's the same e divided and then divided by that coefficient plus c. If k is 0, well, that's saying we have e to the 0 power. And if k equals 0, this is just equal to 1. So that rule isn't going to apply. So that's why they have that in here. If we are taking the antiderivative of a raised to k dx, my guess is this is missing a x in here. then this is equal to a raised to the kx all over k natural log of a, and then plus c. Okay, so those were just our basic rules to help us to take the antiderivative or do integration, same idea, principle, same thing. And then sometimes it wasn't possible to find those integrations. And so we learned a rule called the substitution method. So we just chose some u to be one of the following. So a lot of times how we chose u was we're looking for something that was underneath the square root or root, something raised to a power, something that was in the denominator if it was more than one term, and the exponent of e. Those were all good choices. Another good choice was, and it's not written in here, but if you see the natural log in there, then choose that. Definite integrals, we kind of looked at definite integrals as area under the curve. And first we started, and I just showed you a little bit of this, and we didn't get too much into it, but we would get further into this if this was a calculus for STEM majors. So the indefinite integral from a to b, if we're bounding some area beneath the curve and the x-axis, where that function was above the x-axis, between some value a to b, we could look at the limit as n goes to infinity, and we could sum up those areas of the rectangles underneath that curve and the x-axis. And that would give us the estimate of the area under the curve. So properties of definite integrals, a lot of them hold true, the same as indefinite integrals, but there's a couple extra ones in here that we didn't see with the indefinite integrals. So if our bounds were the same a to a of the indefinite integral of f of x dx, well, then that integration would equal 0. Sometimes we saw, if we're looking at areas, we wanted to split up the areas of where our function crossed the x-axis so that we could see which part would be negative, and we could take that in fact. And so we have the antiderivative from a to b of f of x dx. Sometimes we want to break this up into multiple integration, using different intervals that combine all the interval from a to b. So from a to c, and then from c to b. And the last one was if we flipped the bounds on our integration, it would be the same thing, except that it's multiplied by a negative in front. So the fundamental theorem of calculus was a great rule that helped us so that we didn't have to use these rectangles or a way to estimate the area under the curve. Well, actually, this definite integrals would give us the area under the curve, but this fundamental theorem of calculus also does it, and it's a much easier way to do it. And so we have the integration from a to b of f of x dx. This is the same thing. Well, we could write this as capital F of x with a vertical line, b on top, a on the bottom of that vertical line on the right. And that just is saying that we're looking at the antiderivative evaluated at our upper limit of our integration minus the antiderivative evaluated at our lower bound of integration. We have to have some rules on that to use this, that our function f is continuous on a, b, and f is any antiderivative, capital F is any antiderivative of our function f of x, which is our integrand. Okay, last one in this chapter was the area bounded between two curves. And so if we wanted to find the area bounded between two curves, we had to recognize which curve was on top of one and which curve was on the bottom. And so if we were looking at this area in between here, and this was from A to B, we had to look at which function laid on top. So let's say that this was our f of x function, and which function was on the bottom, which was our, let's say, g of x function. So we would take our top function minus our bottom function evaluated at that interval so that we want to find the area bounded between. Okay, so let's look at some examples. So first example, we have the antiderivative or indefinite integral of 2x times e raised to the x squared power and then dx. And so if you're watching the video, you could pause the video right now, try it, and then unpause the video and see if you get the same thing. So I'm looking at this and we don't know how to integrate what we have right in front of us. And so we have to either manipulate it, which I don't see a way to manipulate it right now, to integrate that. So another way to think of this is use substitution. And we only know how to take the antiderivative of e raised to some coefficient, some number times just x. We don't know how to do it when it's x squared. And so that should clue you in what to choose your u to be. So u is going to be x squared. Once we figure out what u is, we took the derivative of both sides. So du is equal to 2x dx. We solved for dx, so we're going to divide both sides by 2x. We get du over 2x. Then we went back into our integral and we replaced things, what we had chose u to be and what dx is. So rewriting it, we have this dx e raised to the u power and times dx, which is du over 2x. And we choose some value for u. We have to make it so that when we're plugging things back in there, that there's just the variable u in that integrand. We can't have that x and the u in there. And usually when you choose u, you're choosing something that's going to cancel that out, which this does. So we have the integral of e to the u du. So the antiderivative of e to the u is e to the u plus c, because this is an indefinite integral. And we're almost done. All we have to do is go back in and do our substitution of what u is, which is x squared plus c. So our next example, we have the antiderivative, or the indefinite integral of a quotient. So in our numerator, we have the quantity inside parentheses 3 times the natural log of z. And then outside of that, still inside the parentheses, we have that plus 2. In our parentheses, that's all raised to the 4th power. And that whole quantity is all over z times dz. So again, this is something that I don't know how to find the antiderivative of, and so I need to manipulate this. I notice I could expand that 3 natural log of z plus 2, multiply that out 4 times, but that 2 doesn't look like it's going to help me. And I don't know how to take the antiderivative of natural log. But if I just use the natural log of z in here, I have a problem because of this 4th power. This is all raised to the 4th power. And so let's choose what we're going to let u to be, everything inside of the parentheses. And so let's choose u to be 3 times the natural log of z plus 2. And so when we take the derivative of both sides, we get du is equal to 3 times, well, derivative of natural log of z is just 1 over z, plus the derivative of a constant 0, and then dz. So if we multiply both sides by the reciprocal, 3 over z, if we multiply the reciprocal of that, which is d over 3, we get dz, it's by itself, is equal to z over 3 times du. So let's go back and substitute in what we have. And so we have the antiderivative, or indefinite integral, of u raised to the 4th power all over z times dz, and dz is z over 3 du. So notice in here our z's cancel. And we're left with, and we can pull out that 1/3 if you want to. We have a 3 in the denominator, a coefficient of 1 in the numerator. So 1/3 times the integral of u to the 4th du. So we can just use that power rule, add 1 to our exponent, which will give us 5, divide by our new exponent of 5 plus c. We use substitution, and so we're going to go back in here and plug in what u is. So we have 3 natural log of z plus 2. This was all raised to the 5th power, all over, well, 3 times 5 is 15 in our denominator, plus c. So the next example is a definite integral with the bounds from 0 to 1. Our integrand is x times the square root, and underneath the square root, that radicand is 5x squared plus 4. And then that's all times dx. So again, we have an integral that we don't know how to integrate. And so let's use substitution. It's going to be a little different because it's a definite integral and not an indefinite integral, which we were working with before. So one of the keys was looking at what was underneath the radical, if it was more than one term, which this is. So let u be this 5x squared plus 4. Start it the same way, differentiate both sides. So we have du is equal to derivative of 5x squared is 10x. And then we have dx. So our dx value is equal to du over 10x. And now we're going to go back in here and rewrite this. So I have x square root of u, and dx, which is du, all over 10x. So the x that was in there and remaining is canceled out, which we want. We can go through and integrate this and then change this back to what u was, or we can change our bounds now. So this was when x was equal to 0 and x equals 1. So if we have u of 0, so if we plug in 0 wherever we see an x, we get 5 times 0 squared, which is 0, plus 4. So this is equal to 4. So when x is 0, u is equal to 4. So do the same idea. Now let's look at this when x is 1, because that's our other bound. So u of 1, going in here and plugging in 1 wherever we see an x, we have 1 squared is 1 times 5 is 5. So 5 plus 4 gives us, this is 9. So when x is 1, we get u is equal to 9. So changing the bounds now, we've made it so that we do not have to go back and do our substitution after we're done taking the derivative. Before I take the antiderivative, let's rewrite our integrand square root of u as u raised to the 1/2 power. And then we have this 1/10 in front. du. So this 1/10, you can pull it out front if you want, you don't have to, of the antiderivative of u to the 1/2. So adding 1 to our exponent. So 1/2 plus 1 is 3/2. Dividing by 3/2 is the same as multiplying by 2/3. This is a definite integral, and so we have to evaluate this from B to A to B, 4 to 9. So this is the same thing as 1/10 of evaluating 2/3. Actually, let's pull the 2/3 out there. And before we do that, let's simplify. 2 and times 2 goes into 10 5 times. This is multiplication, so we can simplify. And so we're left with 1/15 out here. Now we just have to worry about this u to the 3/2 power. And let's rewrite it as a radical. So this is the square root, plug in 9, upper bound, and then let's cube it, minus plugging in our lower bound. So the square root of 4, and then let's cube it. So we have 1/15. All times square root of 3 is 3, and then cubing 3 gives us 27. Minus the square root of 4 is 2, and then 2 cubed gives us 8. So we have 1/15 times 27 minus 8, which is 19. So our answer is 19/15. So next example, definite integral. We're taking the definite integral from 0 to 2. Our integrand is x squared times the quantity. So inside parentheses is 3x cubed plus 1. And then that parentheses is raised to the 1/3 power, and then times dx. So again, another u substitution. We're going to choose u, what's inside our parentheses. So u is equal to 3x cubed plus 1. So let's take the derivative of both sides. So we get 1 du equals the derivative of 3x cubed plus 1 is 9x squared dx. So solve for dx, divide both sides by 9x squared. We get dx equals du divided by 9x squared. So go back and rewrite it. So right now, this is x is equal to 0 and x is equal to 2. And we have x squared, square root of u to the 1/3 times dx, which is the same thing as du over 9x squared. So our x squares cancel, which are nice, which we need. And let's go and change our bounds to be u instead of x. So let's look at u of 0. So u of 0 is equal to, plugging in 0 wherever we see an x, we get 0 cubed, which is 0 times 3 is 0 plus 1 is 1. So now we have the integral where u is equal to 1 of this. Let's pull our 1/9 out, 1/9 of our integral, u to the 1/3 du. And now our upper bound, so plugging in our value of 2 wherever we see an x, our function of u of x. So we get 3 times 2 cubed. 2 cubed is 8. 8 times 3 is 24. And then plus the 1. So that's a 25. And I was plugging it into this. Okay, so let's now take the antiderivative of u cubed. So bringing our 1/9 down, we add 1 to our exponent. So 1/3 plus 3/3 is 4/3. We divide by our new exponent of 4/3, which is the same thing as multiplying by the reciprocal of that 4/3, which is 3/4. And we're evaluating this from u equals 1 to u equals 25. So let's rewrite this a little bit. So this is, we can simplify this a little bit. 3 goes into itself once, 3 goes into this 9 in the denominator 3 times. And so that coefficient that we're left with out front is just 1/12 times, and now let's evaluate this. And as I'm evaluating this, I'm going to rewrite it in radical form, if that's okay. So it's the cubed root that we're taking. That's not going to work. Okay, cubed root of 25 raised to the 4th power. And then minus, now plug in 1. So we have the cubed root of 1 raised to the 4th power. Okay, so there's actually no whole number I can cube to get back 25. So I'm going to leave it like that. So we have 1/12 cubed root of 25 raised to the 4th minus 1. So the cubed root of 1 is 1, 1 raised to the 4th power is 1. So if you didn't have a calculator on the test, I would allow you to leave it like that. Or if we have access to a calculator, we can estimate this. So if you plug that onto the calculator, what's inside our brackets, I get approximately 72.1, and then multiply by 1/12, we get approximately 6.01. It really just depends on how they want you to round and what decimal place, if they want you to put it in decimal form. So the next example says find the area between the x-axis and f of x over the interval. We're given that f of x is equal to the parentheses, the quantity 3x plus 2, and that's all raised to the 6th power. And the interval is between -2 to 0. So because it's telling me I need to find the area, I have to worry about which piece is above and below the x-axis. And so we want to first see if this crosses the x-axis. If it does, we want to see, is it inside the interval we're trying to find the area of? And so let's look at that. So we're looking at, well, when things cross the x-axis, that's when our y value is 0. So we want to find x-intercepts. And we're going to let y equals 0 to do that, or f of x equals 0. So we have 0 is equal to the quantity 3x plus 2 raised to the 6th power. Well, basically, we could take the 6th root of each side. Whatever we do to one side, we got to do it to the other side so that we can clear this power raised to the 6th power. So 0 equals the 6th root of 3x plus 2 raised to the 6th. So we get 0 is equal to this 3x plus 2. So we can solve for x. Let's get the x to the other side. If we subtract 3x to both sides, we get -3x equals 2. Divide by -3, we get x is equal to -2/3. Okay, so it does cross the x-axis, and we need to see is that inside this interval. And -2/3 is between -2 and 0. So -2/3 is contained. So this kind of funky E means it's contained. It's inside the set of numbers between -2 to 0. So we want to split this up into two separate integrals and sum those integrals. So we want to look at it from the smallest bound, -2, to where it's crossing the x-axis, -2/3 of f of x, which is 3x plus 2 raised to the 6th power. Plus, well, now we're starting at the x value of -2/3. And then we're going to the x value of 0 of f of x, which again is 3x plus 2 raised to the 6th power. And I need to put dx after each integrand. Thing is, I don't know, is this above the x-axis for the first piece or below the x-axis for this first piece? And so there's a couple things I can do to figure that out. I can either plug in values to the left of this, -2/3 and -2. So -1, and I can see if that's a positive number if I plug it in here. Or if I just take the absolute value of each piece that I'm splitting up, well, that would take care of the negative area underneath the curve. So either way, I'm just looking at this. If I plug in negative in here, if I plug any number in here, raised to the 6 is positive. So actually, this actually touches the x-axis and it turns around, and we wouldn't know that. You would know that if you took a college algebra class from us because of the multiplicity. So this actually is going to touch the x-axis and turn around. So we actually don't have to worry about anything in there being below the x-axis. Because anything raised to the 6th power is always a positive number. So this is never below the x-axis. So I did a little extra work because I didn't see that at first. So I can just take this integral from my lower bound -2 to my upper bound of 0. Well, looking at that, I don't want to expand out 3x plus 2 times 3x plus 2, multiplying that by itself 6 times. That would be kind of tedious to me. So I notice I can use substitution here with a little bit of manipulation if I need to. So let u equal this 3x plus 2. So taking the antiderivative both sides, antiderivative of u is 1 du equals the antiderivative of, sorry, not antiderivative, derivative. I took the derivative, but say that antiderivative. Take the derivative of both sides. Derivative of u is 1 du. Derivative of 3x plus 2 is 3 dx. So dx is equal to du over 3. That's one of those mom moments where you tell your kids, do what I, oh, that one is do what I, that would have been a bad one. Do what I do, not what I say. Okay. Yeah, there's my dyslexia, switching things around. Okay, so let's put back in what u is. So we're now, these are my x values though. Let me just put a little note to myself because I almost forgot. X is equal to -2, x is equal to 0 of that integral. And now we have u raised to the 6th power times dx, but dx is this du over 3. So let's change these to u's. And notice that that 3 is in the denominator. I can pull 1/3 out front. U to the 6 du. And so let's go back in here and let's figure out what u to the 0 is. Well, that one's the easier one. Plugging in 0 wherever I see an x, I get 3 times 0 is 0 plus 2 is 2. So when x is 0, u is 2. Now let's look at when x is -2. So I'm looking at u of -2 equals. So I have 3 times -2 is -6, and then -6 plus 2 is -4. So when x was -2, we get a u value of -4. And so now we're in the formula that we can take the antiderivative. We don't have to go back and replace our bounds. So you have this 1/3. Add 1 to our exponent, which is 7. Divide by our new exponent, which is 7. And we're evaluating this from -4 to 2. So we don't have to worry about our coefficients. 1/3 times 1/7, let's pull 1 over 21 out front. And then let's plug in our bounds. So upper bound first, we have 2 raised to the 7th all over 7 minus, and then plug in the -4. So we have -4 raised to the 7th. Oops. I just pulled out the 7, it's just so I didn't have to do that, and then I forget to do that. I already pulled out the 7 and made the 21. So it's just 2 to the 7th minus -4 to the 7th. Well, 2 to the 7th, 2 times 2 times 2, all times itself 7 times is 128, minus -4 to the 7th. Well, negative raised to an odd power is negative. And that will give us negative 16,384. So this is actually a minus, a negative is a plus. So 16,384 plus 128 gives us 16,512. Which, if we rounded, this is approximately 786. Let's just round to the whole number. And we're doing area, so units squared. Now we're looking at an example where we want to find the area of the region enclosed by the following curves. F of t equals 5 minus t squared. G of t is equal to t squared minus 3. And we want to look at this from t equals 0 to t equals 4. We need to figure out what curve is on top and which curve is on bottom. We also need to figure out if these are crossing each other in between t equals 0 and t equals 4. Because if that does happen, if they intersect, one might be higher than the other in certain regions. So first thing I would look at is solve for when our two functions are equal to each other. So when f of t is equal to g of t. So doing that, I get 5 minus t squared. This is equal to t squared minus 3. So solving for t, I first look at what type of equation I'm looking at. It's quadratic. And so in this case, there's a couple ways to solve it. Let's just get everything to one side. That's normally how we go about solving a quadratic. So let's add t squared to both sides and let's subtract 5 on both sides. And if we do that, adding t squared to t squared, we get 2t squared. Minus, we have 3, and then we're subtracting 5, so we get minus 8. This is equal to 0. So I notice we can factor out a 2, and doing so we get t squared minus 4, which is the difference of squares. And so we can factor t squared minus 4 as t minus 2 times t plus 2 equals 0. So 2 is never equal to 0, but t minus 2 is equal to 0 when t is 2. And t plus 2 is equal to 0 when t is negative 2. So we want to see, do any of these bounds, do they fall between 0 and 4? And 2 does, negative 2 doesn't. And so we might have to break this up where one function is bigger than the other. And so we might have to look at it from t equals 0 to t equals 2, and then t equals 2 to t equals 4. Let's look at this. So basically we have some value here at 0. We're going to have some value here at 2. We're going to end our interval at 4. We want to see which one is bigger. So maybe choose something inside our interval here in between 0 and 1. I'm sorry, 0 and 2. Let's choose 1. So how about t equals 1? And so let's go back in there and let's plug that into our function of f of t. So f of 1, if I plug that in there, I get back a value of 5 minus 1 squared, which is 4. Where if I looked at g of 1, this equals 1 squared, which is 1. 1 minus 3 is negative 2. So notice that our function f of x is bigger than our function of g of x in between this interval. So f of x in this interval is bigger than g of x. The equal to part is at the 2. So let's do the same thing. Now let's look at when t is equal to, and this is f of t, and I just put f of x. I thought about that writing out the problem. Maybe I should have just put x instead of t. Okay, so let's choose a number between 2 and 4. So what about 3? So if we look at f of 3, well, plugging in 3, wherever we see a t, we get 3 squared is 9. 5 minus 9 is negative 4. So now let's look at g of 3. So if we plug in 3 into g of t, we have for t, we have t squared is 9. 9 minus 3 is 6. So notice in this interval, our g of t value is bigger than our f of t. So this helps us set up our integrals for finding the area bounded between those two curves. So we're going to have two separate integrals. We have the integral from 0 to 2. This one is where f of t is bigger. So we always have the curve above minus the curve below. So f of t minus g of t dt. And then we're going to go from 2 to 4. And in this case, g of t is bigger. So we're going to write g of t minus f of t dt. Okay, so we actually have to subtract off those functions. So if I have f of t, I have 5 minus, maybe we can do that first so that we don't have to rewrite this integral each time. So f of t minus g of t, and let's combine like terms. This is 5 minus t squared minus the whole quantity of g of t, which is t squared minus 3. So that negative has to be distributed to each term of g of t. So we really get 5 plus 3, which is 8. And we have a negative t squared minus a t squared is minus 2t squared. So for this f of t minus g of t, our integrand here from 0 to 2 is 8 minus 2t squared dt plus the integral from 2 to 4. And now let's figure out what g of t minus f of t is. So our g of t function, this was our t squared minus 3 minus the whole quantity of our f of t, so parentheses around the whole thing of 5 minus t squared. Distribute that negative and combine like terms. So we have a t squared minus a negative, so plus t squared is 2t squared. And we have a negative 3 minus 5, which is a minus 8. So t squared minus 8. dt. Okay, so let's go ahead and integrate and find the definite integrals. So the antiderivative of 8 gives me 8t minus the antiderivative of 2t squared. So 2, add 1 to my exponent, 3, divide by 3. And this is all evaluated from 0 to 2. Plus, and now taking the antiderivative of 2t squared, again, is 2t cubed over 3, minus 8, and this is bounded between 2 and 4. We always put in our top bound first. So plugging that in wherever we see a t, we're going to have 8 times 2, which is 16, minus 2 cubed is 8. But once I do that, I have this 2 in front, so that's 16. So minus 16 over 3. Minus, now plug in 0 wherever you see a t, that's just 0. Plus, so now we're going to plug in 4 wherever we see a t. If you cubed 4, 4 times 4 is 16. 16 times 4 is 64. 64 times the 2 in front is 128 all over 3. Oops, this should be an 8t. Plug in 4, so minus 4 times 8 is 32. Minus, be careful here, I have to subtract the whole quantity when I plug in 2. We already actually did that over here. When we plugged in 2, we got 16 minus 16 thirds. Okay. So let's distribute our negative, and let's come, I noticed really quickly that my negative 16 thirds, and I'm going to have a plus 16 thirds, those are going to cancel. Here, actually, let's just, well, those cancel. So we have 16 right here. This is going to be a minus 16. So those are actually going to cancel. So really all that we're left with is this 128 over 3 minus 32. And so we need a common denominator, which is 3. And so we get 128 thirds minus 32 times 3 is 96 thirds. 128 minus 96 is 32.
Oh, shit.
or 10 2/3. And again, we're talking about areas, so it's whatever unit squared. So same directions as the last one, where we're trying to find the area bounded between two curves, where we're given f of x is equal to the curve x squared minus 4x, and g of x is equal to the curve x minus 6. The difference in this one is that we're not given any value bounded between x values. Like in the other one, I think we were bounded between 0 and 4. Here, again, we need to find out where these two functions are intersecting. And we should find that they're intersecting in two spots. And then we have to figure out which one's above and which one's below. And so if we look at this, we want to find out when is x squared minus 4x equal to x minus 6. So solving equations, you should look at what type of equation and how you go about to solve those. This is quadratic. So we want to get everything to one side of the equation. So let's subtract x. So you get x squared minus 4x minus x is minus 5x. And then let's add 6 to both sides. So plus 6 equals 0. So first thing I would do with quadratics is see if I can factor it. There's no greatest common factor, but I do see that there are two numbers that multiply to 6 and add to -5. So this is factorable. I'm going to factor this as x minus 2, x minus 3. So looking at each factor and setting it equal to 0, x minus 2 is 0 when x is 2. And x minus 3 is 0 when x is equal to 3. And so we have a lower bound and we have an upper bound of our integral. So our integration is going to be from 2 to 3. We need to know which curve is above and which curve is below. And so let's just choose a number in between here and see which one is the bigger number. And so let's look at f of, how about between 2 and 3 is 2.5. So if we look at 2.5 quantity squared, and then we subtract off 4 times 2.5, we get back, this is negative 3.75. If we look at g of 2.5, you can see that's already bigger, right? No, actually it's not. 2.5 minus 6 is negative 3.5. Actually, it is bigger. So negative 3.5 is bigger than negative 3.75. It's closer to the 0. It's bigger. It's on the right. So our g of x function is bigger. So we need to look at g of x minus our f of x function. So we need to make sure that we're distributing the negative to each term in f of x. So we have x minus 6. So distributing a negative to this x squared minus 4x. So you get x minus 6 minus x squared plus 4x. By distributing that negative. Now let's combine like terms, and I'm just going to rewrite this in descending order of powers. So negative x squared, I have an x plus x, 4x, which is a 5x, and I have a minus 6. So we're looking at the integrand of negative x squared plus 5x minus 6 dx. And so now we can take the antiderivative of our integrand. So using the general power rule for each piece, so add 1 to our exponent. So we get negative x cubed over 3 plus 5x squared over 2 and divide by that new exponent. And then antiderivative of a negative 6 is negative 6x. evaluating this from 2 to 3. So let's go in and let's plug in 3 wherever we see an X. So I get 3 cubed is 27, divided by this 3 below, that's 9, and I have a negative out front. Plus, so now I'm plugging in this 3 again, squaring it, I get 9 times the 5, which is 15, divided by the 2, so 15 halves. Minus 6 times 3, which gives us the 18. So that's just with a 3. Now we have to subtract off. Now let's go in and let's plug in 2 wherever we see an X. So 2 cubed, that's 8. And we're over 3, so that's 8/3 with a minus in front. So I have negative 8/3 plus, so squaring my 2, that's 4, times 5 is 20, and 20 divided by that 2 just gives us a 10. Minus, plug in 2 for X, we have 6 times 2, so that is minus 12. So maybe just combine right now integers. So negative 9 minus negative 18, so that's negative 27 plus 15 halves. Minus negative 8/3 right here. This is a negative 2. 10 minus 12 is negative 2. But distributing this negative is going to make these positive. So negative 27 plus 15 halves plus 8/3 plus 2. So negative 27 plus 2. Oh yeah. Is just, okay, let's just keep going. I feel like I have an error in here, but let's just keep going. And then I'll look, unless you guys see anything, let me know. Negative 27 plus 2, so that's negative 25. Plus 15 halves plus 8/3. So I need a common denominator. My least common denominator is 6. So I'm going to multiply this negative 25 by 6/6. I'm going to multiply this 15 halves by 3/3. And I'm going to multiply this 8/3 by 2/2. So negative 25 times 6, that's negative 150. It's all over 6. 15 times 3 is plus 45 plus 16. So my problem is that our area is negative and we should be getting a positive area. So maybe I was wrong when I was looking at what was in between each other. Let me just finish and then let me go back and look at my work. So negative 50 plus 45, that's negative 105. Negative 105 plus 16 is negative 89/6. Talking about area, this should be positive, and we looked at finding the function above minus the one below. So I'm going to pause the video and see if I can find where my error is. Okay, so the error is right in here. When we plug in 3, we get 3 squared is 9. 9 times 5 is 45 all over 2. And so this right here, I had 15/2. So 45/2. 45. Still need a common denominator, but when I do 45 times 3, let's see what that is. It's giving me a 15. That's going to be a 135. And so 135, if I add my positive first, I get this negative 150 plus 135 plus 16. That gives me 151, which is a positive number, which I knew I needed to get. So I knew something was off, which is always kind of nice, right? If you're looking or working on a test or on the homework, you can tell that there was something wrong. You can go back and look for it. And so if I add 150 plus negative 150, I get 1 all over 6. Okay, so our next example, f of x is equal to 1 plus e to the negative x, and we're bounded between 0, x equals 0, and x equals 4, and we're trying to find the area between 0 and 4 of the f of x and the x-axis. So we need to find out if this crosses the x-axis. I notice that this is never going to cross the x-axis, and I know just because of my function e. But if we looked at this and we didn't know that, we could set 1 plus e to the negative x equal to 0. And so looking at this, let's just rewrite e to the negative x. That's the same thing as 1 over e to the x. If we equal 0, if we multiply both sides by e to the x just to clear our fraction, we get e to the x plus 1 equals 0. And e to the x, if I subtract 1 on both sides, equals negative 1. Well, if you look at the graph of e to the x, the graph of e to the x is always above the x-axis. And if we look at the graph of y equals negative 1, those are never going to cross each other. Another way to think of this is taking the natural log of both sides to get this x down. We take the natural log of negative 1, you're going to get an error. What we take the natural log of has to be positive. So this is impossible. And again, I know that this is strictly above the x-axis because any value you plug in here for x, maybe it's easier if you see it this way. Well, 1 plus 1 over 2.718 raised to any number is going to be positive. And so that's always going to be greater than 0. And so we know that f of x is above the x-axis everywhere from 0 to 4. And so to find the area, we're looking at the definite integral from 0 to 4 of 1 plus e to the negative x dx. So no substitution is needed. We can go ahead and take the antiderivative of 1, which is x, plus the antiderivative of e to the kx. So that's e to the kx, which is e to the negative x in our case, all over the coefficient that is in front of our x, which is negative 1. It's bounded between 0 and 4. So we're looking at x minus e to the negative x from 0 to 4. So first thing you want to do is plug in your upper bound, 4, wherever you see an x. So we get 4 minus e to the negative 4th power. And then we subtract off. Now we're going to go in and we're going to plug in 0 wherever we see an x. So 0 minus, well, anything raised to the 0 power is 1. So e to the negative 0, e to the 0 is 1. So let's distribute this negative here. So we really have 4 plus 1, which gives us 5, minus, you can technically rewrite this as 1 over e to the 4th power if we wanted to, or we can leave it like this, 5 minus e to the negative 4th power. And if you wanted to, you could always plug that into the calculator. So 5 minus e raised to the negative 4th power gives us approximately 4.98 square units.